The procedure requires a presentation by the candidate and then a scientific discussion afterwards. Please allow me to introduce the jury members to start with. Starting from the left-hand side, we have Dr. Claudio R from the Universidad Rey Juan Carlos in Madrid, Dr. Raúl Vicente from the Max Planck Institute of Brain Research in Frankfurt, Germany, Victor Egelus, you all know, and Dr. Luis Martinez from the Instituto de Neurociencia in Alicante. So let's start with your presentation, which is supposed to be about 45 minutes.
Thank you, the members of the jury. Thank you all for coming. The thesis, this is my PhD thesis, it's entitled Dynamics and Synchronization of Motifs of Neuronal Populations in the Presence of Delayed Interactions, and it was directed by Professor Claudio Mirasso. So we are going to concentrate on the scale of neuronal populations, because this is a very important scale. The neurons are considered the building blocks of the nervous system. However, most of the information processing in the nervous system for the functions for the important functions of the nervous system occur at this level, at the neuronal populations. So this is so we concentrate more on this population, on this level, and also we are going to focus on synchronization, because this is an important pattern of dynamics that occurs in the brain, and this occurs also between distant brain regions in the presence of delayed interactions. So that's going to be our focus on this thesis. So I'm going to skip many details that are in the thesis, and I'm going to concentrate on a main thread. So an important feature of this that could be used to understand most of the results relies on the anti-phase synchronization of two oscillators coupled with delay, with a certain delay. So when they are coupled with delay, they tend to synchronize in anti-phase. So that's an important characteristic that we are gonna that can be understood. The result can be understood based on this fact. So one can extend these two couplet oscillators and use three couplet oscillators. And in this case, the two first neighbors synchronize in antiphase, tend to synchronize in antiphase. So 1 and 2 will be in antiphase, 2 and 3 will be in antiphase. So 1 and 3 synchronize in phase. So that's the dynamic relay, and we illustrate here with the Fatkin-Huxley model. So in this case, nodes 1 and 2 synchronize in antiphase, and 1 and 3 synchronize in phase at zero lag. And well, that's a very general phenomenon, and it was first proposed by Fisher and collaborators. And this is called the dynamical relay. This is the optical setup of this open chain. So the outer nodes are nodes 1 and 3, and this is the central relay element. So nodes 1 and 2 and 2 and 3 synchronize with a certain delay, and nodes 1 and 3 synchronize in phase with the maximum of the cross correlation at zero lag. So they used semiconductor lasers, and this was done in experiments. They also showed in simulations, and also in motifs of neurons. So this already showed that the phenomenon is very general. And afterwards, this was also shown in many other systems, highlighting the general aspect of the dynamical relay. And we are going to concentrate on the dynamical relay in neuronal systems. So, synchronization it's found in the brain, and it's thought to be an important dynamical feature. So it occurs for between distant regions, even when there is a long delay in the connection, which is much longer than the internal time scale of the neurons. And this is also associated with some behavior. So in this case, the synchronization would be the link between the activity of specialized and segregated regions to integrate the dynamics between different regions. So synchronization is thought to be an important feature for binding the activity to integrate this activity of distant and segregated areas. And we are going to study the dynamical relay in the brain. So asking whether the dynamical relay would play a role or could explain this synchronization that is found in the brain. So the outline of the main results that we are going to explain now starts with the dynamical relay in cortical populations. So they have already shown, it was already shown that the neurons, the motifs of neurons synchronize at zero lag, but we would like to extend to cortical populations because that's an important scale in the brain. So then this was very general, and then we concentrate on more specific circuits. In this case, the thalamocortical circuit first, because the thalamus is thought to be an important relay station of the brain, the natural relay station of the cortex. And then we consider the hippocampus and the interaction of the hippocampus with the cortex. The hippocampus is one of the most studied areas, and the interaction of the hippocampus with the cortex is not so much studied. Most of the interactions are considered just with prefrontal cortex, and we are going to extend to look at motifs. We extend a bit this motif and consider other cortical areas, and look at the synchronization between the cortical areas mediated by the hippocampus. And the activity of the hippocampus occurs most at slow frequencies in theta band. So we look at the synchronization in slow frequencies in theta band. And then finally, we come back to the dynamical relay and try to consider what's some essential behavior that's going on that would explain the dynamical relay. So we call this the resonance-induced synchronization, and we are going to see this later. So each one corresponds to one of the results chapter, each topic. So just to start with the results, we first consider this is a very important problem of the different levels. So we are trying to extend the idea of the dynamical relay from single neurons to populations of neurons. So once we change the scale, some important phenomenology can appear, new behavior that wasn't found before. So it's always important to check whether this could occur. This is robust in respect to this aspect. So in order to do this, first we consider the robustness of the small motif of neurons, and then we consider the populations. So in the motifs of neurons, we consider the Hodgkin-Huxley model. So it's a biophysical model. So we look at the membrane potential of the neurons, And well, this is it's a bit it's four there are four coupled differential equations or linear differential equations, so they are not very easy to understand, to simulate and to understand. It takes a long time. So when we consider small motifs, it can be used. It's good to use this model, which is more realistic. But once we try to extend this to populations, we'd like to have a more simplified model. So the dynamic relay in single neurons occurs very fast. So if we consider neurons oscillating and we couple them at time 0, after a short transient time, the neurons are already synchronized at 0 lag. The outer neurons are already synchronized at 0 lag. So this shows that the dynamic relay is fast. It could take place at a fast time scale. And also the delay there was just fixed, and we can also consider distribution of delays. So instead of using just a single delay, consider many different delays, which is a way of considering getting close to more realistic. What happens more realistically in the brain, because there are actually thousands of axons connecting different nodes. So if we consider a distribution, we are mimicking this difference, this diversity in the connections. So we look at the synchronization of the outer nodes, considering this distribution of delays. And we use this order parameter, which is 1 when the outer neurons are synchronized at 0 lag. So we use a gamma function, a gamma distribution, which has two parameters, the shape factor and the scaling factor theta. So for most for most of the times, for most of the k factors, and with an average delay that changes in the realistic, what one would expect, in the range that one would expect by the experiments. So in most of the times, this synchronization is robust, and so this shows that this dynamic relay is very robust with respect to the distribution of delays in the connection. So it's not very specific that one has to tune very well the delay that occurs more than just that. So it shows already that it's very robust and generic. And we would like to show this, to extend this from motifs of neurons to motifs of populations of neurons. So we consider thousands of neurons in each population, and we use this standard recipe in which 80% of the neurons are excitatory and 20% are inhibitory. And the dynamics of each node, we consider a much simpler model, which is almost the most simple model that one can use, which is the integrating fire model. So each neuron is described by just a very simple differential equation, and there is this reset when the neuron reaches a threshold, and it stays at a certain value, certain reset value for a refractory period. So this very simple dynamics of each node allows us to study large networks. And again, the dynamic relay is robust with respect to populations of neurons. So one can look, for instance, at the raster plot, which shows the neurons and the spiking of each neuron. So after one can connect each population and connect the populations at a certain time. Here is marked by this green line. So after a short transient period, the outer populations are already synchronized at 0 lag. So the first I mean the first neighbors, the populations 1 and 2 are synchronized in anti-phase, and populations 1 and 3 are synchronized in phase. And here the cross correlation is found by the number of coincidences between random neurons on each population. And if one considered a different motif instead of putting the dynamic relay, the relay of node 2, and consider just the connection between 1 and 3, one sees synchronization, but 1 and 3 synchronized, but in anti-phase. So it's important in order to have zero-lag synchronization to have the dynamics mediated by a relay population. So this shows that the dynamic relay can be extended from neurons to populations of neurons. And this model is very universal, it's very general, and has a overwhelming robustness, very robust. However, there is a limitation because it's due to the fact of being very general. It does not represent special circuits, and we'd like to see two particular circuits, which is the thalamocortical circuit and the hippocampal cortical circuit. We first consider the thalamocortical circuit, which is the strongest candidate to mediate the cortical synchronization. It is bidirectionally connected with the cortex. It occupies a central position in the brain, so the delays from the thalamus to almost any cortical area is very similar. And it is considered a relay station of the brains, of the cortex. There are many loops between the cortex and the thalamus. The thalamus receives external stimulus from sensory areas. So the sensory stimulus excites the thalamus, and the thalamus sends this. It's the gateway to the cortex, so it sends the excitation to the cortex, and the cortex excites back the dorsal thalamus. So this is the thalamocortical loop, and the thalamus, the dorsal thalamus is very well connected with the reticulus, which is inhibitory, and it's very. So the thalamus would be those two areas, and this layer is for a given sensory stimulus, but there are actually many different parallel sensory stimulus, and so each layer is almost independent in a certain sense, because the dorsal thalamus of each one is independent. They do not connect directly to each other, but connects with the reticulus, and the reticulus connects with different ones, and the cortical areas do connect with different. There are many cortical connections. So we would like to consider a very reduced thalamocortical circuit. So we'd like to look at the synchronization between two cortical areas and mediated by the thalamus. So the dorsal thalamus receives external stimulus from the sensory areas, and the reticulus and the two cortical areas receive external stimulus from other brain regions. And this is the thalamocortical circuit for a certain type of stimulus, of sensory stimulus. And we also use a very simple model. So the cortical areas are also described by the same recipe: 80% of excitatory neurons and 20% of inhibitory neurons. We consider the thalamic region just by excitatory neurons, and the reticulus, the inhibitory neurons. So this is the excitatory and inhibitory regions of the thalamus. And one can look at the dynamics of this thalamocortical circuit. So if the external stimulus over the thalamus is large enough, the thalamus synchronized, the reticulus synchronized, and the two cortical areas synchronized with respect to each other. But here we cannot see it very well because there is a large variability in the data. But one can try to view this looking at, for instance, many trials. So we used 100 trials, and we averaged over 100 trials the cross correlation. So first of all, we see that the two cortical areas show multiple frequencies, one in the beta range, which is a bit slower, and one larger frequency, gamma range. And then we consider that the zero-lag synchronization would carry some information, so this would be the signal, and the average amount of coincidence would be the noise, just what is expected by chance. So one can look at the signal-to-noise ratio, and this, for the thalamocortical circuit, we will consider has a local maximum, which optimizes the signal-to-noise ratio. And this occurs if the cortical areas are connected or if they are unconnected. And the feedback from the cortex to the thalamus is very important. If one removes the feedback from the cortex to the thalamus, this enhancement disappears. So this could be used as a control of cortical synchronization. So depending on this ratio of external stimulus over the thalamus, the cortical areas can show no synchronization or they can show synchronization. So one can say that the thalamus promotes and controls long-range zero-lag cortical synchronization. And it's also important to show this control because excess of synchronization it's a pattern of shown in abnormal brain activity. So it's important to promote, but it's also important to control to avoid excess of synchronization. So we return to the same idea of extending the general dynamical relay to other circuits. So in this case, we consider the hippocampal cortical circuit. And this is another candidate to mediate the cortical synchronization. And the hippocampus is active at slower rhythms, so in this case, theta band. And it's associated with memory functions, and memory relies on precise spike time because of plasticity and STDP rules. So if there is no precise spike time, this would mess with these memory formations and memory activity. And also another motivation for us to consider this circuit was that our collaborators in Seville had some experiments. So they found some traces of dynamical relay, and we could see whether this could be, whether we could model the dynamical relay in this for this system. So they were looking at three regions, two cortical areas, the visual cortex and the frontal cortex, and the hippocampus. So they had local field potential simultaneously recorded in the three regions, and they found that for most of the times, in the sliding window, we can look at the correlation in the sliding windows. In most of the times, the two cortical areas synchronize at zero lag, and the hippocampus is delayed with respect to the two cortical areas. So this would be a signature of the dynamical relay. And comparing the activity, the pattern of activity of the mouse when it was moving or when it was awake but just at rest, one sees much more variability in the data when the mouse is at rest. So this motivated us to do some modeling. So each region is also a neuronal population, and it receives external stimulus with a certain, each neuron receives external stimulus with a certain rate. And there are long delays in between the populations. And in this case, we are looking for the oscillatory activity in theta band. So integrated fire was not the most appropriate model for us for using these neurons. So we needed a more flexible model. So in this case, we used the easy cavity model, which has two equations. It's fast to simulate, so it's similar, but then it has one advantage that it does not show only regular spikes, but it also shows bursts. And so we consider the hippocampus as most of the neurons in the hippocampus acting in bursts, in the burst mode. So we connected them so they synchronize in the theta band, and we consider the cortical areas mostly irregular spike. So those are just some random neurons. They create some random neurons in each area, and this is the average membrane potential of the population. So the hippocampus shows nice theta oscillation, so it generates theta oscillations. And the two cortical areas do not show prominent oscillatory activity. But then when we connect them, the motif, we see that the two cortical areas synchronize, oscillate and synchronize at zero lag. And we model, we use the same model for the active and the passive states. The only difference that we consider the input rate in the active state a bit larger than in the passive state. So we compared the average membrane potential with the local field potential of the experiments. And we would like to comment on the motif that we used. So we are using this motif because the two cortical areas are connected. We cannot avoid this connection. But we can look at the role of the mediator of this relaying element. So if it's receiving and sending input, and when it's just sending input to the cortical areas, indicates that the two cortical areas are just independent. So the synchronization between the two cortical areas only occur if there is input and feedback from the mediator. And in the other case, the two cortical areas do not synchronize. So it's important to have the input and the feedback from the hippocampus to generate a synchronization of the two cortical areas in the theta band. So we can compare the local field potential they have with the average membrane potential of the neurons in our simulations. So our simulations show good agreement with the experiments, but in this case, the two cortical areas we use just they are very similar, but we can break the symmetry just considering a different delay here, so we can get closer to the experiments. So the dynamical relay promotes long-range zero-lag cortical synchronization in theta band. And it was the first experimental evidence of dynamical relay in the brain. So I hope I have convinced you that this is an important problem, the problem of changing the scales. Because now I want to convince you that this is a very important problem. Instead of using thousands of equations for each node, as we were doing before, which is the most straightforward way of considering populations of neurons, here we use the reduced model for each node. So in this case, the neural mass model. So we have for each node just 3 equations. It's a reduction. So we are going to look at the average membrane potential of the excitatory pyramidal neurons in each population. And this reduction allows us to look carefully at the different motifs that appear. So the motifs are the single building blocks of complex networks. And one can look, for instance, in the motifs of three nodes, the dynamics of the different motifs, what happens. So it was seen that the matrix visual cortex, for instance, show all of the motifs appear, and some appear with a probability much larger than expected by chance. So this perhaps indicates that some motifs have show some dynamics that are more important than others, or for some reason this occurs, and we'd like to understand this better. So we, with this simple model, we revisit the structures. The dynamical relaying originally proposed was this motif here. So this is node 1, 2, and 3. So we'd like to actually look at the common driving, which has been considered as an important dynamics of the brain. It was, in our idea, it has been overestimated because once one would see synchronization between two regions, they would say, okay, they are just receiving common input, so that would explain the synchronization. But we'd like to show that this common driving is not really efficient to synchronize two regions, and other motifs are much more efficient. In particular, this we knew already, that's very efficient. It's motif 9, it's the dynamical relaying. And our idea is that this common driving is improved when there is a resonant pair, when the mediator, the driver node, is synchronized. It's sending synchronized input to the other two nodes, so they synchronize much easier. So this resonant pair would induce the synchronization of the two outer neurons or outer regions. In this case, we are looking at considering cortical regions. So the presence of this resonant pair, we claim that this is important and would enhance the synchronization of nodes 1 and 3. And coincidentally, motif 9 is the motif that appears mostly in the macaque visual cortex, and then motif 6 is the motif that occurs second more often. So perhaps these two motifs share some, I don't know, have some important dynamics for the cortex, for the brain. So we'd like to understand this better. So the common driving motif M3 shows the nodes 1 and 3. They do not synchronize typically, and nodes 1 and 2 do not synchronize either. So the cross correlation has no prominent peak. But the other motifs that has a resonant pair, motif 6, motif 9, and motif 3 plus 1, shows nodes 1 and 3 synchronize at 0 lag, and nodes 1 and 2 synchronizing anti-phase. So this can be better seen in the cross correlation. So the highest peak, it's at 0 lag between nodes 1 and 3, and nodes 1 and 2 are synchronized with the anti-phase. So this is just one single example of the dynamics, but one can look this better, doing an average of many trials with different initial conditions. So we are comparing here the common driving with motif 6, 9, and motif 3 plus 1, and the three motifs shows the driver node synchronizing anti-phase with another node, in this case with node 1. In this case, this is synchronized with node 1 and 3, and these two synchronized with 4. But in the three motifs, node 2 is synchronized. So in this case, the motif M3, the common driving, do not show large zero lag synchronization between nodes 1 and 3. for the different coupling strength. But the other motifs, even for very weak coupling, already shows large synchronization of nodes 1 and 3. And this happens in the presence of delay in the interactions, and also in the absence of delay. So it's very consistent with the different delays in the connection. And in this case, all connections have the same delay. And we also consider the other two motifs, M8 and M13. So those two motifs have also at least one a pair of mutually coupled nodes. But M8 is receiving a common derivative that has 1 and 3 mutually connected. And M13 is M9 plus this connection, this bidirectional connection between nodes 1 and 3. So compared with motif 3, they are very similar in the presence of delay, but in the absence of delay, if the coupling is sufficiently strong, motif 8 and motif 13 do synchronize at zero lag. So this occurs only if the delay is negligible. And in this case, if we compare motif 9 and motif 13, for instance, we see that this connection disturbs the synchronization of nodes 1 and 3. And in this case, there is a bit of variability with respect to the delay in the coupling, because the absence of delay helps the synchronization. So we think that this resonant pair, it's important to have node 2 synchronized in order to induce parallel synchronization of nodes 1 and 3. So this resonant pair would be fundamental dynamical building block. It would be underlying the dynamical relaying. So our main conclusions are that the dynamical relaying is a overwhelming, robust mechanism. The thalamus promotes and controls cortical synchronization. The hippocampus mediates data band dynamical relaying and can also be compared to experiments. And the resonance-induced synchronization underlies the dynamical relaying. And those are other works I also did in this time period of the thesis, but were not included in the thesis. And thank you very much.
Thank you, Leonardo. We will continue now with the scientific discussion, and we will follow an order which is given by the distance that people have reached to come here. The longest distance was by our defender, so you can start.
First, I would like to make a comment, and is that I think the interaction is just excellent. I come from a department of neurophysiology. I can tell you that most of the theses that are written there don't have the coverage of the biology as you have in your thesis. So first of all, I would like to congratulate you for that. And it's clear that you made an effort to read the biology of the system and to understand the anatomy and the physiology and the evolution and the development. So congratulations for that. Just a comment on the introduction is that I think I missed a little bit that when you talk about receptive fields, it's very important that there is normally a topographic relationship, right? So networks map to network normally because of the sensory systems, perhaps with the exception of propulsion. So maybe if you want to add one or two paragraphs from that. Also, I have a comment on the thalamocortical network that you studied. Basically, you mentioned that controlling the thalamus could be a way to say, okay, now these cortical areas should engage in synchrony or not. Basically, you always talk about some ascending input, just controlling the rate input there. But this is a comment also that the cortex itself can control that, because layer 5 and 6 correlate also to the reticular nucleus and to the thalamus, and themselves they can say, okay, now we need synchrony with that or not, or maybe something to study maybe for the future. A question I have is also when you model the thalamus there, you don't put interneurons in the nucleus that we call thalamus. Is there any reason for that? You put everything on the nucleus, but not on the thalamus.
Yeah, no, that's just a reduction. The inhibitory part is just transferred to the reticulus. Just an approximation, a first approximation is reduced model of the thalamus circuit. But we can also add that, but I don't think that would be
probably will not change much. So you talk also in your thesis about phase frustration, which I think is a very important topic, right? Because at the end these motifs are could be embedded in a larger network. And you familiar also, I guess, with the communication through coherence hypothesis by Pascal Fries. What are your views on that? Let's say, do you think it will be compatible then? Mechanisms like communication through coherence when this is embedded in a larger network, or at least it limits the efficacy of the communication?
Yeah, I mean, that's a big question. But I don't know, but maybe the structure depends on the dynamics. So maybe in a structure that would give rise to frustrated dynamics, if one node is not active for some reason, it's inhibited for some reason, so this would allow synchronization, but then when this node is active, it would inhibit the synchronization. So actually this could be an important thing to look at and to explore and see whether this could give rise to. So this actually could for sure give rise to flexible dynamics. And actually I started to work with this, but I didn't have time to include it in the thesis. But yeah, that's an important issue.
Also, the thalamocortical network, when you see the cortico-thalamic connections, so the feedback connections, you saw that the cortical regions do not synchronize so efficiently. Do you think it's a matter of just giving higher input rate to the central node? And if it would be the case, then it would be compensated with higher input from external? Or is the feedback really necessary?
Yeah, I think it's not so simple as just enhancing the input. I think it's more that it changes the dynamics, the internal dynamics of the thalamus. And this is also, I mean, can be also seen in the last part, because the interactions is important in how it interacts. I would say that this, so it receives the feedback. So when it's synchronized, when it's enough to synchronize the cortical, so the feedback that it receives also doesn't need to be really strong, but just synchronize inputs. So this would enhance the synchronization of the thalamus that would lead to larger synchronization. So there is some resonance in the circuit.
So it is essential then?
Yeah, so I think so. So that's why we see this local maximum. It's not just the common driving. The common driving is the last, I mean, the most strong input, so we will see it enhances also the synchronization, but this local maximum, I think it's a resonant effect. Also, when you study the hippocampal cortical network and you model the active states as an increased input to the hippocampus, 6%, what is the biological motivation, or why you did it like that? Yeah, no, that's just very, very intuitive. There are some references that people see some, for instance, power law behavior, and it depends on the state. So for an active state, the activity changes a bit, so increases the activity of some regions. But but the idea, I mean, one can have some experiments showing this sort of behavior. But one also, it's a bit intuitive to show actually this motif is not isolated. There are many other regions. It's a whole network, and it's actually impressive that this small motif can show reproduce any dynamics of the experiments. So if there is a whole network, so for many tests, this will not be very active, but in some cases it will be more active. So suppose that when they are active, they are receiving more input, and this doesn't need to be much stronger. It's just a very tiny difference, but will be enough to show the different behaviors. But there are other alternatives to also reproduce the same dynamics.
So measuring axonal delays is very difficult, and some people claim that actually between areas could be actually faster because of the myelin and the local thing. What do you think will happen if you reverse the magnitude of the delays? So what we call long range connection will be actually fast, what is local will be actually slow.
Oh.
You have any intuition?
Yeah, but I don't know. Yeah, I mean, in this case, when the connectivity is very large, the delays are a bit important to define the clusters. So the clusters are also defined by the delays. I'm not sure if this is straightforward to put it backwards. And yeah, that's something to look at. But I'm not sure if do you think it might be enough that's a good question. I'm not sure that could be. But yeah, this has to be done. We have to look at that.
I'm also, as a final comment, also like to mention that the coverage also what you did, because you didn't show here something you did on the 3D computation and everything, so you really take a big scope on the different levels of the neural system. So we would also like to mention that. Congratulations for that. And I think for the moment, yeah.
Thank you. Thank you, Javier. Okay, thank you. Congratulations for the work. It's been a pleasure to hear and also reading the thesis. It's very well written and very well organized, so congratulations for this work. Also congratulations for the presentation, very clear. Normally people don't clap until the end, but they were so enthusiastic with the presentation that they couldn't wait. I was clapping also, so, so thank you very much. And now time for nasty questions. Okay. At the beginning of the thesis, you say a sentence that for me it was a little bit, I don't know. I will read it, okay? In completely segregated systems, the units are independent, and there is only randomness. What do you mean with randomness? I mean, you're saying that in a completely segregated system, you have randomness due to the segregation?
Yeah, no, well, that's very well explored by Olaf Sporn in his book. So, well, they have this theory of complexity, so they define complexity as so they say that a very segregated system, the units are independent, and when they are all connected, but they are too much connected, they act just as a single unit. So randomness in the sense that so if they are independent, each one is doing its own dynamics and its own.
Yeah, because the next sentence says, in a completely integrated system, all units behave identically, and there is only irregularity.
Yeah, well, that's the other extreme. So we are trying to put different extremes. So in one extreme, just consider the neurons, for instance, that are all unconnected, so they have their own dynamics or not, but they are not connected. So there is no relationship between one another. And in the other case, just not weak coupling, that we are considering very strong coupling. So everything is very well connected, so that would be a good approximation to consider everything as just a symbol.
But not regular.
Yeah, no, this regular and irregular, it's an idealization of some other system. So I think at the end of the paragraph, I compare order disorder. So it's trying to make this more general. So trying to consider more general systems. So other transitions. So I will consider to. Okay. Yeah, and I know. Well, we have to discuss this.
Okay, another question in a similar way, also in the introduction, and this is a sentence that I am really against. So maybe I am a very open person, so maybe you can. Okay? This is the well-known small world property of the cortex, which promotes economy and efficiency in brain networks. Economy and efficiency and small work. Please explain me that.
I mean, okay, you can.
Yeah, but I think I have some citations at the end. No, I mean, I'm comparing what you have said, so it's not my claim, but it's actually, I think it's exactly for the community. So, well, I don't know, there are many words, so small words in the brain, and each one has thousands of citations. But yeah, I'm saying that.
Yeah, this is the problem. I mean, what I think is that you can have a small word property and not being efficiency or economy or whatever. So it's completely different. But it's okay. Just
in particular, there is this book that I'm rather influenced by this book. I've been working with
I
don't know.
I have read the book. I like it very much, but there are some things that I don't like. Okay. Going to the chapter 4, when you study the dynamical relying populations of neurons, this question is question. How can you assume that the central system is not forcing the outer systems? I mean, since it is bidirectional property, how can you assume, or how can you assure that it is not just forcing, it is synchronization? You understand?
Not really. Who is forcing whom?
The central system is forcing the
thalamus, you mean?
No. Just it's chapter 4.
Oh, okay.
We didn't write.
Yeah.
So you have a central system, you have two outer systems.
Oh, I see.
Then
The
outer
central
systems are
system.
synchronized, but not forced. So how can you assure that it is not forcing? Because I mean, the central system, if it increases the coupling to the outer systems, probably it will force the system to follow.
Yeah, no, in this case, we haven't just took away the feedback, but we've done in all the other chapters. But I mean, I can say that it's not so efficient to just remove the feedback. But in this chapter, for instance, we haven't showed the dynamics without the feedback, but we have done from there on. So every other system, we just remove the feedback and see what happens. And without the feedback in all the other systems, we see that, especially in the last part, we just the common driving is not. So this forcing is not enough, typically in the weak coupling regime. Mm-hmm. So if this is strong enough, for sure, some synchronization will occur. But maybe it depends.
So it's a matter of the strength.
I'm not sure, because maybe it depends on the initial conditions or things like this. But when there is a dynamic relay, it's much more robust with respect to the initial conditions. So one do not need to tune very well the system in the beginning to see, because then the system evolves to the synchronized state really fast.
Okay, next question. I think that term zero-lag synchronization appears also in the thesis, not in the title or in the alternative title when you say it will be dynamical relying on neuronal systems. But my question is, I will try to explain it, is that is it necessary zero-lag? I mean, or first, if it is necessary in the brain zero-lag synchronization, and next, zero-lag synchronization is a particular case of relay synchronization, because you can move from the zero lag just having different relays. So zero lag has something that is necessary to be in the brain, and also it is different zero lag from, for example, a delay lag due to relay. I mean, relay synchronization, I understand it is more general. Zero lag is a particular situation or a different situation, or a special?
That's a good question. Well, we concentrate a lot in zero lag synchronization because it appears a lot in the literature, especially in the cortex. But also there are other systems in which the phase locking is also important, in particular the hippocampus and the prefrontal cortex. So they do not see zero lag in particular. Actually, what we do is to extend this to a larger motif and see also zero lag synchronization between two cortical areas. But the phase locking, we also reproduce this phase locking that is well known in the interaction between the hippocampus and the prefrontal cortex. But
And-
yeah, I don't know. Most of the literature in the cortex refers to zero-lag synchronization, but there is also other types of synchronization. But we concentrate more often on zero-lag synchronization.
And do you think that in the brain, you can only get zero-lag synchronization by means of a relay system, or there are other ways?
No, there are certainly other ways, but this is a very robust and general mechanism that could be playing a role in many systems or many circuits.
Okay, and it's robust also.
Yeah, it's very robust.
Concerning chapter 4, also talking about the populations, you have 3 populations, the relying population of neurons and ones. Did you say what happens if you change the sizes of the populations? I mean, I think you use always the same size.
Yeah, no, in
And I
this
think
case,
that-
yeah, I mean, the dynamics scales a bit with the size.
Maybe
of-
it's not a very realistic case to have the same size. I mean, can you, for example, change the size and tune another parameter in order to? Did you try that? Or?
Yes, well, before, this is just a final result, but before reaching this, in this case, for instance, in each case of populations, there are a lot of parameters, always, because there are many unities. So there is, the strength of the connection, so there is the strength of the connection inside the population, the strength of connection between populations, the number of connections inside and in between populations. So I guess it's very robust. I mean, this is big enough. And the difference would be one could find the same result just doing this strength of the connections or in a larger systems.
So you think that, for example, you can have the outer systems of different sizes. For example, one 5 times higher, larger than the other.
I think so.
By tuning coupling or.
Yeah, I think this would be possible. Actually, this is robust with many respects, and I think this would be robust as well to a certain extent. I don't know how far this could be, but for sure, to a certain extent, it would be robust.
And what about the topologies inside the populations? Did you try different topologies or just random connections?
No, this is a very generic behavior. We are not particularly interested or trying to mimic any specific cortical region, just to show that populations might behave that way. But yeah, one could extend the level of details can always be increased. One can always put some more details, but yeah, that's one thing that must be balanced in the number of details, because when you have many details, you typically do not understand the system very so well. So it's good to have this look in this perspective on a simple system.
Okay, in chapter 5, concerning the role of thalamus in the zero lag, I was wondering if the thalamus is necessary. Is it possible to obtain zero lag synchronization only with 3 cortical regions?
Yes, I mean that was the generic system that was in the previous chapter, and this was just what we're interested in the thalamus because it is already thought as the natural relay station of the cortex, and the thalamocortical loops are very important. And everyone, there are many studies on this circuit because it is an important circuit. But yeah, of course, the other cortical areas would also change the dynamics. In the last part, we are more interested in just cortical network. But the thalamus would be the first and the most prominent subcortical area to play a role in this cortical synchronization.
Okay. In chapter 6, concerning the role of hippocampus, you measure the cross-correlation between areas. And did you measure or try to measure the phase synchronization? These were amplitudes and just check the phases?
Yeah, I mean, we have the experiments. So, I mean, the system is rather complex, and we have the experiments, and we are trying to get closer to the experiments. So, in order to look at the experiments, there was this filtering in the database. So, we tried to make the same procedure, or as close as possible, to try to look and to compare with the same things. I mean, try to as we could. So, I mean, we haven't done this, but I mean, our skills, because we are trying to be close to the experience. But yeah, I mean, this could be done as well.
Okay, so for me, that's all. Congratulations and good luck in the thesis.
We continue with those documents. I would also like to congratulate you for the thesis, and I had a really good time reading it. I appreciate the effort you put into writing the introduction. I think it's really nice. And also, I think I will look back at this thesis for a long time, trying to understand my own results in neural networks. So I appreciate that also. Thank you very much. The presentation was also pretty good. It's excellent. I could follow it from beginning to end, so it's also a plus.
Yes.
And I had a lot of questions that were already touched by the two other members of the committee, but I want to elaborate a little bit more on them, if you don't mind. I'm not going to follow any regular order, but in the hippocampus, for instance, one thing that we know by very, very recent results is that neurons that respond to particular features, the so-called concept neurons or whatever, they tend to have fixed latencies regardless of the type of stimulus that triggers that response. And we know that visual inputs take longer to process than auditory inputs, for instance, but the latency of the hippocampal neurons is fixed. Do you think that such a model could actually explain that, explain why, regardless of the input, a neuron on an outer node would have a fixed latency?
I'm not sure if I understood everything. So, what is just the final question?
Okay, so you have, imagine that in this case, the hippocampus is not your central node, okay? It's one of the outer nodes.
Yeah.
Imagine that. But still, it could be part of a motif, a similar motif, right? And one of the things that we know now is that neurons within that outer node respond at a fixed latency regardless of the type of input that triggers the response. And we also know that different types of sensory inputs have different latencies. So do you think that a similar mechanism could explain that fixed latency? So it could be useful for timing of responses?
I don't know what yeah, I'm not sure if I have an answer for this question. But this latency you are considering from the stimulus is being present and then the activity
to the response of the neuron. Yeah.
So this is fixed. Yeah, I mean probably this refers to the path that the information is passing,
Exactly.
but I'm not sure.
In the visual system, you have huge delays compared to the auditory system, for instance. But the response of the neuron is exactly at the same time, whether you show a picture or you say the name of the concept, right? That is triggering the response.
Yeah, I'm not sure if I would use these, I mean, our results to explain this, or if I would use this as a motivation for doing what we do. Because we consider fixed delays, so I don't know, this would be one more argument for us doing what we
So
do.
then
We just
let's
assume that.
rephrase the question then. When I do this, you hear and see the clapping at the same time. Your perception is simultaneous. Do you think that this would explain that? Even though the delays in both pathways are completely different.
Yes. Yeah, but that's the integration that's going on afterwards. And
Right, but would you expect to have one of these M9 or M6 circuits actually?
yeah, that's the binding by synchrony proposal. That somehow this synchronization would be important to integrate, to bind these activities from different regions, from different paths.
So I guess that the question is, would you have simultaneous perception without zero lag? Is that possible?
Yeah, that's a much bigger question. I'm not sure if I can answer that, but yeah, but that's an important question.
And then another issue that you touched upon, but I don't think that you actually went deep enough into it, neither in the thesis nor in the presentation, is the trade-off that you have between specificity and robustness or synchronicity. There's another common difference between different cortical areas. I don't know if I phrased that correctly. For instance, you have to be one is pretty well organized in domains where cells have very similar response properties, at least to some very specific features of an image, for instance, orientation or the area of dominance or whatever, retinotopy and so on. And so all cells within a neighborhood, at least to a particular feature, could in principle respond synchronously. That wouldn't degrade your perception. But if you go to hippocampal regions, for instance, or cortex around the hippocampus, or IT, for that matter, the inferotemporal cortex, then the organization is much more scrambled. So neighboring neurons can respond to very dissimilar features of an image. So synchronizing neighbors should in principle degrade in that area, degrade your perception. So I was wondering whether you expect different behaviors depending on the type of cortex that you're probing and the local structure of the cortex. And that has to do with the local structure that you chose in the different populations. So I don't know whether you can comment on that.
Yeah, I mean, no, I mean, that's also important inquiries that we can do and we can hear about. But I mean, our results are in a different level, and I don't know how to translate for sure because we are not really. I mean, that could be a perspective how to look at the spatial temporal pattern inside each population, which for sure occurs. So in view one would be more receptive fields, much more easy, linear and straight, and in the other regions would be much more complex. And so this is also related with the levels in the hierarchy. So.
Right.
But yeah, I'm not sure. I mean, one can wonder about this and one can study this deeper. But
okay.
yeah, I mean, that's a big problem, but I don't know how to.
Okay, no problem. I have another question also. How much time do you need to build up this synchrony? Or how many spikes would you need? Right? Do you have an intuition about that? So how rapid the process is? Do you really need to fire a lot of spikes? Because as you go also from the input areas to the areas that are higher up in the hierarchy, fighting becomes extremely sparse. To the point that in IT and other regions, you can get 1 or 2 spikes per neuron in response to stimulus. Would that be enough to actually get this type of behavior?
Yeah, this depends a lot on the dynamics of the nodes and on the excitability of each node. So if one node is very excitable, it's close to the threshold
right.
somehow, and if the strength is strong enough, so perhaps few inputs would be enough.
Mm-hmm.
But I mean, I would say that typically some inputs, several. But well, I mean, we have seen that in this dynamic programming mechanism, this can be fast, not instantaneous, but fast.
Mm-hmm.
So hundreds of milliseconds, that would be a physiological time scale that this could take place, or we believe that this could take place at this scale.
Then that's consistent with a fixed latency of 300 milliseconds for these responses, which is what I was trying to figure out. Because 300 milliseconds is huge, it's a long latency. Why would you wait for 300 milliseconds if you can make it fast? Maybe it's because you need to do something else before. Okay.
Yeah.
Then, one thing I wasn't sure about well, also another comment about the interneurons in the thalamus, that you have local interneurons, and the funny thing is that the local interneurons and the reticular neurons, the neurons, are completely different. So they have totally different dynamics and constitutive structures and everything. So it might be interesting. And it might be interesting because also what you are discussing that the thalamus has a potential or as a possible relay of cortical activity or synchronization for different cortical areas. But most of the time, different cortical areas have a different relay in the thalamus. So it's not the exact same nucleus in the thalamus that is projecting back and forth to different cortical areas. But what is, or could be common to different thalamic nuclei is the shell of reticular neurons. So could they act, having just a shell of reticular neurons that is shared by different thalamic nuclei, could that be the central node? Could that make the thalamus, different nuclei in the thalamus behave as the central node? Is that possible?
Yeah, I don't know the answer, but that's an important question. I mean, that's in the list of the perspectives somehow, not exactly like this, but also to consider, for instance, two independent thalamic nucleus, right. And perhaps the dynamic relay could be playing a role, so this would be the outer nodes, and this would be an idea if the reticulus, right, being the mediator of these two outer nodes.
It would be equivalent to having two populations in the central node that are not connected between each other. They do not share many of the inputs to cortex, but they share the inhibitory neurons. So the inhibitory neurons would actually synchronize them, and they would act. Yeah,
this is the only region in the thalamus that connects between, and this would be some integration of
that's interesting. Okay, and then I think this is going to be my last comment. Okay, you lost it. Have you explored, or how much have you explored the possibility that feed-forward, feedback connections between the central element and the nodes have different delays, extremely different delays and strengths, and how much that would, so that would actually cancel zero, or move the, right? What would you expect?
So if this is the mediator and these are the outer nodes, so we are considering the going back and forth. So we saw that it's very important one branch, compare one branch to the other. But if this is tau 1 and this is tau 2, this is not very important to have this difference. Actually, in the thalamocortical circuit, we have asymmetry.
Of the two branches have
but here it's different. So if this is tau 1 and tau 2 and tau 1. So in this case, this would be important. If actually there is some difference here between this and this, for instance. So the outer nodes do not synchronize at zero lag, but synchronize at a certain.
Right, yeah. And can you compensate for that with strength or not? Or can you compensate for that with different strengths?
I'm not sure if the strength compensates the delay. I think they are different things. I think we cannot mix both things.
Okay. But for instance, when you talk about the motif, I don't remember, the M3, which is a common input without feedback, that is not good for synchronizing, that does depend on strength, right? I mean, if it's really strong, they will synchronize.
Yes.
Okay. Thank you very much. Really appreciate it.
Thank you.
Thanks. So, first of all, I really enjoyed reading the thesis. I mean, my knowledge on brain is almost zero, and I have, the first chapters is a very nice summary with basic models. So that was very, very helpful for me. Also, I think in general it's very well written. It's hard to find typos or mistakes in grammatical errors. In some places it's very easy. So I think that tells that you have very lot of attention to the writing. So this is also very good. So of course, everybody misses something when one reads a thesis. In my case, for example, it could be more, let's say, physics content in the sense of, for example, how you measure correlations, different ways, linear correlations with nonlinear correlations, also how you measure phases when you have spikes. Here, I think you use one that is a linear interpolation. but I mean, there are more, and I don't know what are the difference, or whether you will get different results or not. So there are many things of this kind, and also some mathematical design. So I think it's a lot of extensive numerical simulations, very detailed. But the insight you get sometimes with mathematics and with some models, I think is something interesting. And I'm not saying that you should do it if you don't have time, or if this is what you have done. But I think there are some words out there that could be very helpful in order to make sense or more sense to what you are doing. And I think this is a little bit what is perhaps missing. So coming to some questions. My first question is about vocabulary. So you call in chapter 7, you call resonance induced. I don't know what that synchronized. What is the resonance?
Yeah, this is, I mean, this is very fancy title for
well, could be fancy, but I mean, it's, what is the resonance?
No, the idea is that the node 2, the driver node, should be synchronized. So there is a resonance in this, well, or not synchronized, but well, later on we show that this should be under the effect of some synchronized pair. So the resonance would be this translation of these anti-phase synchronization.
There is no resonance. I mean, there is nothing that is resonating, right? There is not an internal scale that is resonating with the delay. It's nothing. It's basically what it means that there are two knobs that are connected bidirectional. That's what I mean. In fact, when they are isolated, they are not resonating. They are anti-phase correlated. Right?
Yes, but I mean, they prefer to be in a certain frequency, so they don't. Yes.
Okay, so that's the first one. The second one is about relay. So, I mean, for me, relay is what you see in the Olympic, right? So somebody is giving a relay to somebody else, and this guy is giving the relay to the next one. But here, and in some cases, the picture is okay. It's more or less kind of cartoon and could help, but it's not really the case, right? Because it's you and me and you and him. So but I don't really see what we are relaying all the time. So the concept is a little bit confusing to me. I mean, in some other motifs, it's even harder to understand what it is a relay. But perhaps it's just.
Well, the mechanism was called dynamical relay.
I know.
So starting from there, no? So there is a relay from the mediator. So yeah, there's this bidirectional connection. So this would be connected with both. So it depends on the type of connection.
So my question is, do you think that this is just a fancy name, or there was something deeper there that I missed? But he has something to say.
No, that's the point. In this last chapter, we are trying to figure out what's going on underneath. But I mean, I'm not sure how would the more complex systems like chaotic oscillators, if in chaotic oscillators M6 would be enough, or to what extent M6 would be enough to synchronize the outer nodes. So perhaps the M9, the two relay, the two bidirectional connections is important in some systems, but in those systems in particular, this is not the case. But well, I don't know. That's one question to but the relay, I mean, I think it's a relay. The Motif 9, I think it's a relay. I don't know why you don't like to...
Well, I don't say what is being relayed.
As the semantics of the word relay.
Yeah, that's it. So, and the next question is also semantics, I think. Is what is information? Because you use information in many places. And for me, it's just signals. Right? So there is a spike, and this is a signal that goes to the network. So, but you are using processing of information. So when a signal becomes information, or
no, I'm just assuming, because we know the functions of the brain, that the brain is processing something, signals that are being processed, and consider this as information somehow, because it's important to process this. But yeah, but I'm not using a very well defined word for.
So you're using as a synonym. And
yeah,
is that
I
you are talking about the brain.
Is when I would like to stress more about the functioning of the brain. I'm not sure if all the time I've been doing that, but I would say that the idea of information would be more to relate this function of the brain and signal when I'm looking at the dynamics of neurons that I'm not sure what they're doing, but I know that they are transmitting signals.
Okay. So let me come back to a previous question. So order disorder, that sounds like phase transition, critical point.
Exactly.
But here it's just the opposite. This is order. Right? When you synchronize, it's order. So if in one side you are saying, even in the words of somebody else, that the brain should be at the edge of dark, and you are paying attention only to synchronization, the disorder is not disorder, and it's not even at the critical point between blah blah blah. So how you? So is you expect to be there synchronized, not synchronized? The brain sometimes is synchronized and sometimes is not, or it's always in the critical. So what is your picture of the thing?
Mm-hmm. Well, that's interesting. Well, my picture is that phase transitions and everything, it's related to large systems. So we are looking at motifs, which are small parts of the network, but one can look also at the big picture of the network. So, if you consider a big picture and there are small motifs that can be synchronized or not synchronized. So this would be one way of connecting, of relating segregated regions. But inside a big network. So the network in general would not be all synchronized, it would be doing many things. So we are looking at the exchange of information.
The problem there is that you are telling me, well, you look somewhere else, probably there is no synchronized. But the guy who is studying this part will tell you, well, this part is synchronized and the other is not. So I have some problems there. But I will come to that later, to the aggregation and everything. So, one of my question is whether synchronization is everything on the brain, right? Because, you are just measuring synchronization, you are asking question when the thing synchronized, and it seems that everything that the brain has to do is synchronized. But our brain is synchronized, and the small brain are also synchronized, and the C. elegans can also synchronize. So, but in principle they are very different. So, what else is missing? So, probably this could also be, it's a general view, probably it's also some open question for the future. But for me, it's fine, and it's something that one has to understand, and there are a lot of experiments, but I'm missing something, because I cannot understand that the brain is only something that synchronizes different parts, or perhaps it does. So
no, definitely the brain is not just synchronizing, this is just one perspective that we assume, and we work on this perspective in our work, so our study assumes that this could be important, so, and this is
so you think that this is really important. So imagine that you have an example, so you know the C. elegans, and in a few years you will know how the brains are connected to each other. And you can do simulation of all the neurons. So what the thing you are going to do is just to simulate that in a big computer and see which neurons are synchronized, and that will tell you everything about the brain.
Definitely not.
And then, what kind of information is telling you?
I don't know, but I'm not sure everything the C. elegans is doing either, but if one is expert in C. elegans, maybe one can relate the dynamics of the neurons in the C. elegans with the behavior of the C. elegans in a specific, tasks, or if the C. elegans is doing some specific. But this is what people have been doing in other systems, and looking at synchronization and trying to relate this with behavior, with
So they have found something with 300 neurons in the CLNs. They have found something exciting about.
Yeah, I'm not sure if
Because I know communities, I know many things about that, but well, at the end of the day. Okay, so the other thing. Okay, fine. Let's go to an easy question. So you have one of the previous transparency. It's really easy. I will tell you where. It's so when you compare the experiments with well, you can put it and the rest of the people can see. When you compare the experiments with the simulation.
Hippocampus.
So there, the experiment is done. So there you see, I mean, this is coincidence, so you count the number of peaks, right? So you see that there are zero lag correlations, a lot of a maximum of zero between B and F. And then you see two peaks. And they are not at the same delay. So my first question is, how can you do it? And not numerically. So if me and Ingo, we are a zero lag. Me and Ingo are 10 milliseconds delay. And he should be 10 milliseconds delay. So how do you do it?
Yeah, I know what you mean. No, but I mean, you are talking about the experiments? Or?
Well, I'm talking just about the figure. So in that figure, what it's telling me is that the maximum between two guys is zero, between the other two guys is 10 milliseconds, and the other is, I'm putting just, is 30. And we are three. So how can it be?
Yeah. Well, the answer for this is that the measure was done with some precision that was not very good. So
Yeah.
the precision of the local field potential was 5 milliseconds. And so when we look at and there is also the filtering. So we're looking at time series that has been processed. So
what you're telling me
this
is that it's a
has
program filtering?
15. No, this has 15 milliseconds and this has 30 milliseconds. So the maximum maybe it's at 20 milliseconds. So it has to go to one or to the other.
So that means that probably a zero is not zero also.
Yeah, the zero could be.
And the second thing is that when you do the numerics in the next page, you are able to reproduce that. And there you don't have limitations on precision.
No, but I put the same precision to compare.
And,
I don't want to compare one thing.
and you didn't bother about the fact that
Yes,
not at the
but
maximum.
these experiments cannot be done so
But you have the
easily.
numerics.
I had the numerics, but I'd like to compare it with the experiments.
So you want to make the same mistakes and make the same.
Exactly.
Okay. So the next question is about the robustness and the motifs and all these things. So coming back to complex systems, so what is telling me complex is what you say here. So it's more than the sum of the parts. And now you come and tell me, okay, I'm going to study motifs. That this is a small part. If this is not contradictory? I mean, if complex system is a complex system, and you are telling me, no, if I study this part, and they put it together, I get something else in reality. And now you come here and tell me, no, I'm going to study motifs.
Yes, I mean, there are two extremes, and there is a lot of things in between, and we have to understand what's in between. So that's one way, one approach.
But that was the approach of the reductionist approach, right? And it's supposed that in complex system, what you said that in the control exam.
Yes,
this
but-
approach shouldn't work.
No, it's not
No?
shouldn't work. One must be careful.
And you what?
No, one should be careful to extend, to borrow the knowledge of small parts to big parts. But this can be done. I mean, one can try to build from the small to the large.
Yeah.
But yeah, the idea is that this is not straightforward. It's just not scalable.
So it's not straightforward that your result should apply to the brain, because these motifs are embedded in a larger thing
That's
with a
true.
lot of feedbacks, with a lot of input, and that
There are much
maybe
more things
that
to do.
was isolated when you put overall, it doesn't work.
Yeah, I mean, there are much more variability. Much more things are going to happen. But I mean, this case, for instance, of the hippocampus illustrates that at least some feature.
No, in this case of the hippocampus is only 3-4 nodes.
Yes,
isolated populations.
I'm looking at these in the experiments, but the whole network is there all the time.
No, in the experiments it's clear. What I mean is that your modeling is only considering this. What I'm saying is that you are missing a lot of things, and you know that this lot of things could affect them. In fact, you just reduce to the adic interaction, and you try to extrapolate, and this is what this doesn't work even for the 3 motifs, right? So why you should expect that the 3 motifs work for the whole thing?
I mean, it's not.
I mean, let me be clear. I mean, I think this is a very nice a proposal and a mechanism that is plausible to explain what is happening. But my question is not that. My question is, okay, do you expect that this, when it's embedded in a larger system like it is, you should expect that this phenomena will still be working there or not?
Yeah, no, we don't know, but we expect that some things will remain.
Which ones?
Yeah, I mean, that's something that must be tested. It's not easy to extrapolate. But for instance, in the last chapter, we look at the dynamics of 2 nodes, so we try to understand things based on 2 nodes only. So we try to understand the dynamics of 3 nodes.
Let's go to base to the 2 nodes. So you say that some of the families are very frequent, right? This is what you saw in some of the pictures there. So yes. I went and I recovered my papers and also yours. But if you compare the frequency with respect to the random case, this motif is not so frequent. And in fact, I mean, the original paper by Allen, M3, M6, M9 are underrepresented with respect to the random case for the neural system. This is the original superfamilies by Uri and the second one.
Sorry? No, but that's... So.
And this is for the neurons. And they are underrepresented. This is the CLX.
Yeah, the CLX. This is cortical.
Okay, so let's go to the cortical. So let's go to the sports paper.
Yes.
So here also it compares the 2 cases, right? And it, for example, for the 6, right? Well, it's more or less as frequent as in the random case. And
but motif 9 is much advanced.
Motif 9 is the only one that in the case of the macaque is much advanced. That's true. But the rest are not. So, do you still keep your claims?
No, I mean, that's...
Or this is the macaque, because we are different. Right, our brains.
Yeah, no, what's the question?
No, the question is that I understand reading your thesis that you are saying that the ones with the resonance are more frequent, and an explanation for that is because this is giving more efficiency, more robustness to the 0 lag time synchronization. But I'm saying is that, well, maybe 9 is overrepresented, but the others are not. And in fact, there are others that don't have these kind of things.
Yeah, no, this is not proof. This is like a motivation. So this, we see that 9 occurs. So we are not proving that 9 occurs because of this. That's just something that could be checked and a motivation for studying motif 9 better and try to understand. I mean, we are far from explaining this. We cannot explain this without results. But this motivates us to study this motif.
Okay, and with respect to these motifs, there are several models that have been analyzed mathematically. That some 0 lag synchronization, also instabilities that apparently in your models they don't show up. But in basic models you see that some solutions are unstable for some delays. So it's one basic question is, why don't you see instabilities in your simulations? Because they don't show up for the models you are studying, and the others are too simple and they show that, or it's because the parameter values you are using are not far from the instability.
In general, for the populations, things are more robust than for single unities. So
But this is something you know or something you have
no,
observed?
yeah, that's empirical fact of simulating a lot. So I have some intuition, and that's I don't know, that's my intuition about the system. But yeah, I mean, that's one limitation of the thesis. We would like to, I mean, before chapter 7, we are dealing with very complex systems, so it was difficult to get much insight, mathematical insight. And at the end, we find a simpler system. And at this point, I was really eager to study these more simple systems and try to get some more insight and stuff. But I haven't done it. I haven't.
No, but I mean, there are papers there, so we don't need it.
Yeah, but your paper is not.
No, I mean, Ingo has many papers on the stability. So anyway, so about robustness, the first, there were questions about different sizes, and I think that could be something important. There are about topologies. I mean, something that I disagree. I mean, as you don't know how the thing is, you just take random as the general case. Well, the random is as general as a two-dimensional lattice, so they are not a single network that is random. But anyway, so they are with hierarchies and things like that. I think these are open questions that. But the thing is the following. So imagine that you have a relay connecting C1 and C2. How many cortical areas we have? 60? Something like that?
Yeah.
So you have 60 of that. So you can have pairs of 60. That means a lot. So you have the thalamus with many of those. And it seems that if your result is robust, that means that you will reach synchronization. But that means that you will have reached synchronization between C1 and C2, maybe C1 and C3, C1 and C4. I don't see a mechanism to control that, right? And also the complexity of the thalamus just for controlling that, I think, is very expensive, right? Well, I don't know.
Yeah, there is a cortical network. The thalamus is subcortical region, so that the cortical network it's large, has many nodes, but the thalamus is not connected to many regions.
Areas.
Yeah, but the thalamus is not connected to many areas.
So that means that there could be areas that are not zero synchronized.
Of course.
Well, I don't know. I have no idea.
Yeah, no, there are many things going on.
So even that
just a particular case.
So no task can synchronize to specific areas. This is your claim. That there are a couple of areas that are impossible to synchronize. This is what you're saying. It's a question.
I didn't understand.
No, what I'm saying is, my question was, you have 60 areas and you can couple between any two pairs, because you could do a cognitive task, and eventually these two areas could be synchronized. You should have the same mechanism in the thalamus, this with this, and something separate this with this, because these are different cognitive tasks. So this is huge. But I was understanding that you were telling me that there are a couple of areas that they are never formed synchronized. So my question is, that seems very complicated, and I don't see a mechanism that prevents synchronization, because you don't want to have all the areas synchronized. So you should have a mechanism that is telling you, okay, these two, yeah, they should be synchronized, but not this and this. And I don't see a clear way of how to control that, because even the mechanism that you propose in chapter 6, I think, is a little bit, because if I have this area synchronized by some other reason, because this is embedded somewhere, I think that this is going to be able to synchronize the other two. So the mechanism should be something different. So my question is, what kind of mechanism do you think? That,
yeah, I mean, this is under discussion. There are many.
Just tell me one.
One
mechanism that
besides
controls, that avoids synchronization.
That avoids.
What?
That avoids synchronization?
Yeah, because I mean, see, you want always these two cortical areas to be synchronized, you just put it together, right? So you want to have situations where this is not synchronized with this, right?
Well, I don't know, there are inhibitions, for instance, but depends on the region, so that would be, the inhibition are more local. So, but yeah, I mean, one region could inhibit itself, I don't know, but not inhibit different regions, typically. But yeah, but if there are, I mean, that's an important question of how to control the synchronization. There are a lot of diversity, there are adaptations, so one neuron skip will not spike.
But the question, well, I will let that here. But the question is more general, because whatever you build it should be there all the time, right? So if you propose a mechanism that is able to synchronize teacher's area with the control inside, then how the control, so that's the difficulty. Right?
Yeah, I mean, this control is in a fast time scale. There are other intrinsic controls working in different time scales. So adaptation in the synaptic strength can change with time as well. So in order to keep synchronized, the strength must be active there. But this occurs so there are many channels that occur that it depends on slower time scales. I mean, things are much more complex than the simple model we are studying here.
Okay, thank you. So first of all, I'm happy to join the congratulations for this very nice thesis. I was impressed by the depth and breadth reading it, and as others have said already, one senses immediately that you have put a lot of effort into formulating and writing this thesis. Furthermore, I would like to acknowledge that with this thesis, and you realize that already from the discussion, you make a stand in a very controversial field and area. Controversial in many aspects, controversial in the sense of what we just had a discussion, a motif approach, reductionist approach versus complex network theory, controversial in the sense of is synchronization an important mechanism in the brain at all, so rate coding versus temporal coding, controversial in the sense of microscopic versus mesoscopic macroscopic coding. So I think one has to also see the work in this context, and I think one of the important things has been said by Louis, saying that if the thesis provides inspiration to go back to experimental data and see, do we find certain fingerprints in the experiments, or can we design experiments that can clarify question, verify or falsify, no matter what, it will be definitely a big advance in the understanding. So I think that is something I wanted to mention needs to be acknowledged. Many of the questions that I had already been addressed. And I would like to pick up certainly on the discussion that Victor started, which is the motif approach versus the complex network theory. And I think I would like to have a bit more polarized and clear view from your side, saying also how it connects to the different levels of modeling, so microscopic versus mesoscopic versus modeling, and where does then the different theories come in and how do they connect? And are they controversial approaches or are they complementary approaches? Yeah, no, I mean, there are a lot of controversies, and this makes the field more exciting. So, I mean, that's my view of the field, and it's very exciting to see all these discussions and people they're not just not caring about this, but they're discussing and trying to figure out what's going on, what's behind, and what's important there. Well, I do not have a position. I can move, I can do different things. So, I mean, I'm in this motif, for instance, we try to understand the system, and we are trying different perspectives, and try to so which one works better? And at what level does the reductionist approach come in, and at what level does the complex network approach come in?
So each level has good things and limitations. So it's a trade-off there. One has to be careful to study and to choose which level one. It's the art of the modeling. So one have some behavior that we would like to understand, it's fundamental to see it, and it's not immediately. I mean, one would not see this immediately. Sometimes, which is the best level to work on. So
I'm asking because in most things that you've done, you've used the motive approach on the mesoscopic level, and you used actually random connectivity, some kind of complex network on the microscopic level. So maybe with that hint, can you elaborate a bit more on what your take is on that?
yeah, I mean, that was important, but I mean, I've been working a lot on that, so I saw all the limitations of that approach. So I was already trying to look for different scales. So in this case, this reduction at the end helps us to see with a different perspective. So we can move better, we can change better the structure in this case. Otherwise, one can do also, but it consumes much more. It's time consuming. The simulation takes much longer. So there are much more parameters to tune, and that seems easy afterwards, but it's not easy to do because it's an interactive process. We know what we are kind of looking for, the type of dynamics we are looking for, but we don't know which parameters will give rise to that. So we have to simulate and then return and see, no, it didn't work, perhaps if I change this will work. So we have to do this actually many times, and if this takes a long time if we have a long time, we have to wait a long time to see the results. I mean, this process can take very long, so it's always good to reduce this time, so we can tune better and we can find the regime that we are looking for easily.
But now you explain why you've been using, for example, a motive approach on the mesoscopic level, complex networks approach on the microscopic level. But what you show here on the transparency is on the microscopic level, right? So how does that connect?
This mesoscopic. This is areas.
This is connectivity between areas?
Yeah.
Okay, then
It is an aggregate.
Yeah.
So here you aggregate times different areas.
Coming back to also another question that Victor raised. Certainly as a tool you've been using numerical simulations. And he mentioned that certainly also analytic approaches exist. Can you comment a bit on to what level analytic approaches might be helpful and where you see the limitations of those? So would it be the next step here to include such approaches, or what would hamper or
I think in this case would be very appropriate, actually. But yeah, if we are using a very complex system and very complex dynamics, many equations, so one has to reduce a lot in order to get any.
But what about, for example, heterogeneity?
In which?
Well, for example, in the approaches that have been followed analytically.
Yeah, I mean, since we are studying things that are new, we always start with the most simple version, and then we are building that. I mean, from that knowledge, we can move to a more complex situation and be understanding this in this line, from this line. But yeah, I mean, there are some systems that have been studied, but I'm not sure. The point is that we are working with different systems in a different level. I mean, it's weak coupling. So, for instance, I don't know. But Victor and you two have worked with Kuramoto model. oscillators, but they are not in the weak coupling regime. So I don't know if it's straightforward to make this, to borrow what was the knowledge of those systems to more complex, to different regimes.
Okay, final question from my side. It's a conceptual question. You discuss this thalamic circuit that you introduce with the reticulus as having the possibility to control the synchronization, also to switch it on and off. Can you generalize that in a network connection, a network motive that in general would allow you to build systems independent of neural systems in which you could easily control the synchronization, also in the sense that you mentioned, certainly yours is already a bit more complicated approach, but would there be also a kind of reductionist approach if you want to go beyond the simple system which just permits synchronization to a system which permits synchronization and where you can control synchronization? How would such a simple motive look like?
But are you talking about neural systems or
not necessarily?
Yeah, I think it would be similar somehow. I mean, if you want to do this with lasers, I think it's straightforward.
Could you sketch it? How such a configuration would look like?
Can I borrow the picture you have already?
I don't know. I don't have a picture.
No, but this one.
Yep.
No, I don't know. I would guess the input over here. If we can change the input over here somehow of these mediators, no, the relay station. So I don't know if this you can add some other input here. Oh.
But that wouldn't fulfill the requirement that Victor formulated, that you have to be able to be selective independently whether you want to synchronize or not.
Well, those two regions, if there is a hub connecting many regions and you want to select just a few of those. Yeah, no, this is limited to synchronize or not all the other nodes, like, we saw the other day the hub presentation.
Because how would you interpret, to boil it down to a simple question, the role of the reticulus in your calculations? So why did you introduce the reticulus, and what was really the additional functional role that it introduced to your motive 9?
Yeah, I mean, the reticulus in this case would be better understood, as Luis has pointed out, if it was to connect different thalamic regions, because this has this connection with different thalamic regions.
That was not something which was included in your model?
No, this is just the most simple piece of thalamocortical circuit that one could look at two cortical areas and see whether they synchronize or not. So yeah, I mean, the idea would be probably to the reticulus would be more important if there are more than one thalamic nucleus. But in just one, this is just making the inhibition, which one cannot ever avoid. Pretend that does not exist, because it's very well connected with the thalamus. But yeah, maybe if one considers just the interneurons, or just more interneurons in the thalamic region, this would be similar. So I don't think this is very. We can change it.
If I can add something here, I guess that if you have the reticular force, just to continue with the example, the inhibition being dynamically modulated by different cognitive functions or tests or whatever, and that actually has different impacts on different populations of the thalamus, and that's exactly what you get. You get synchronization sometimes in to given areas and not other times, simply because of that modulation. But that's just a proposal.
So it would be the input to the reticulus.
Right.
Yeah, the ratio of the input in both areas is the important factor, not just the time, but the relationship between the input between the two.
So that was from my side. Any more questions from the jury members? So let me forward therefore the opportunity to any member or any attendee with a PhD is allowed to ask questions now as well. If that is not the case, you have the opportunity now to leave the room so the jury can.